phosphorylase? Yes? What does it do? There you go. Now, so we'll breeze through that a little bit. So I'll focus mostly on ATP synthase. Okay. There were blank faces in lecture yesterday when he was going through stuff, so I wasn't sure, but I wasn't on your all side of the room. So, okay. So real quickly, I do want to touch on the Q cycle because there's one thing we didn't talk about last week, and I want to make sure you guys are familiar with it. He went over it a little bit in lecture. So last week I gave you the basic equations for each of the complexes, right? In order to not make the discussion confusing, I left off part of the Q cycle. So in reality, it looks more like this. Whoops, cytochrome C oxidized. Okay, so before we didn't write that there were two QH2s plus a Q, because one of those, this Q is regenerated. So there's a net of only one QH2 used up. But we're going to talk about this for just a minute. Okay, so the full reaction for complex 3 is this. Okay. What happens is in complex 3, what are the electrons being transferred to? So QH2 is the electron donor. What's the electron acceptor? Yeah, it's up here. This is the acceptor. Okay. So electrons are being transferred to this. What is the issue with transferring electrons from ubiquinol to cytochrome C? How many electrons do each of them carry? How many electrons does ubiquinol carry? Two. How many electrons does cytochrome C carry? Yeah. So, the way this works is that one electron gets transferred to cytochrome C, but then there's this extra electron. So in order to not waste the potential from that electron, what happens is actually inside complex 3, this is going to be an extremely simplified drawing, you have a QH2 that comes in, and then you have just a ubiquinone that's sort of sitting there in the complex. So one electron goes down to QH2, to this Q and makes it a semiquinone. So now it's got a radical ion on it. And the other one goes to cytochrome C and makes it reduced. Does that make sense? So the electrons are split. One goes to cytochrome C, one goes to a ubiquinone that is sitting in complex 3, just kind of bound in a different site. So now this is a semiquinone. It's got an extra electron on it. So this QH2 leaves. A second QH2 comes in and binds, does the exact same thing. So we get a second QH2 that comes in. Again, you get a cytochrome C that's reduced, and you add another electron onto the Q that's sitting in there. Okay. So what this does is it then, actually let's use colors. Okay. So, sorry, I've already started color coordinating and I'm going to make it really confusing. So these hydrogens get pumped across the membrane. Okay. The hydrogens from ubiquinol, from the two different ubiquinols, that's where these 4 hydrogens that get pumped across the membrane come from. These hydrogens that are being pulled from the matrix come along and bind to this Q to generate QH2, and this QH2 goes back into the Q cycle. Does that make sense? And so you get a net of 1 QH2 used for for each round of the complex 3, right? So you actually put in 2, but then you make 1 more, and so you have a net of 1. So does that make sense?
Does that QHD get released from where it's bound, or is it just...
This one? Yeah, it does. Yeah, so in the Q cycle, you have your Q pool, your ubiquinone pool, you have ubiquinones and ubiquinols. And so once this is released, another ubiquinone comes in and binds there. Make sense? Okay, cool. Other questions about this? Okay. So, I mean, it's explained relatively well in your book. There's a nice little picture. I may have even wrote down the figure 18.2, kind of has a nice little graphic representation of this, if that helps. All right. So I wanted to talk about that because we didn't go over it last week. Okay, so what we are going to do now is we are going to talk about ATP synthase. Because we kind of breezed over that, and maybe you guys understand it well enough, but I don't want to assume you understand it well enough. And also you guys seem to think you want a little more information. So, all right, give me back any extras because I printed enough for you guys and my Monday section. Give me those extras, Danny.
Nice try.
This is my extremely well-drawn representation of the ATP synthase.
Hey, it's pretty good.
It's very lovely. I tried to find a blank one online and couldn't, and finally I gave up and just drew it. Okay, so I'm going to draw this on the board so that we can talk about it and stuff on the board too. But while I'm doing that, I want you guys to work on labeling all of the different little subunits that are there. Okay? Does that make sense? What you need to do?
The one day I don't have my book. What? Oh.
How are you guys doing?
Okay.
Okay. Doesn't matter how you're doing because we're going to go through this anyway, so you'll figure it out. Okay. All right. What is this giant green thing in the middle of the membrane?
7.
Huh?
I
I heard people say things and then they all got quiet again.
That's rotation.
It's the rotating, part. What's it called? What's the subunit name? The big green thing. Yes. So this is the C ring made up of 10 to 14 C subunits. And it provides the motor force. Well, I guess maybe that's a bad way to put it. The protons provide the motor force. It's the big thing that rotates. Let's just put it that way. Rotate. I can't spell. Okay. What drives its rotation? I just said it. Protons. And where do the protons enter this equation? A subunit. Where's the A subunit? Yeah. So this is the A subunit. Okay, protons actually we're going to use black. Protons enter in from the cytosol side. They enter in down here. They go in and they bind to a C subunit. When that binding occurs, it causes the C ring to rotate by one. And then so, this one will now be present. And then a proton will come in and bind. And so basically what happens is this goes around, and then the protons eventually come out of the A subunit into the matrix. This is the matrix. This is the cytosol. Does that make sense? So the protons come in through the A subunit, bind to one of the C subunits. That causes a rotation in the ring by one subunit. Now there's an empty subunit that's available for a new proton to come in and bind. Once you make a almost full circle, right before this one comes back to this position, when it's here, that proton actually is released through another channel in the A subunit into the matrix. Does that make sense? Okay. All right. What is this funny little brown thing?
Beta subunit?
It is is it sigma? Is that sigma?
No.
Don't know you guys know
I
your
think
groups.
that's Ada.
Is it Ada? Okay. We're going to go with what Dylan says. And we're also going to check this marker because it's dead. Okay. So we don't know a whole lot about it, but it's connected to this C ring. To C ring and the gamma subunit, so I just gave that away, but you guys probably already knew it. C ring and gamma, and rotates. So the C ring is what's rotating, but this is directly connected to it, so it turns with it. So which one's the gamma subunit? The pink thing in the middle. This is the gamma subunit. You guys are like, come on, Letitia, we already know this. So again, it's connected to C ring. And what else does it do? Great, it's this thing that's connected to the C ring that turns with it. Why do we care? What does it do? Yes. So it causes conformational change. In the alpha and beta subunits to aid, I guess, is the right word, ATP synthesis. It doesn't cause the ATP synthesis to occur, it just changes the conformation so that then the beta subunits can synthesize ATP. Okay. What other ones? Where is the B subunit?
Is it the orange one?
It's one of the orange ones. Which one of them?
Oh.
It's very smart. Leave this watching. Yes. So this is the B subunit. There's actually two of them. The book doesn't actually state whether or not they're dimers, but I imagine they are. But there's two B subunits. Then you have, and I can never draw lowercase delta. Then you have your delta subunit. I think that's delta, right? Delta. Okay, these connect the F0 and F1 portions. Okay, so this middle part, this is F0, this part down here is F1. So basically they connect the membrane anchored parts with the parts that are sticking out into the matrix. All right, so now we have the alpha and beta are the only two that are left. Take up tons of room. Okay, so this is where that beautiful little flower that I drew for you guys comes in. Okay, how did I draw it? Okay, so while I'm drawing this on the board, I want you guys to identify which of the, so the alpha subunits are there, they're responsible for part of the ATP and inorganic phosphate binding, or ADP and inorganic phosphate binding, but they're not what is directly involved with the conversion of ADP to ATP. So we always draw the ADP and ATP in the beta subunit. So the alpha subunits are there, it's a heterodimer, it matters, but when we talk about it in this class, we talk about the beta subunit and its activity. So there's 3 different subunits that look slightly different. Those are the beta ones. Identify which ones, what's bound to each one, and what state they're in. So there's the open state, the top state, and the loose state. So work on that while I'm drawing this on the board. Which ones, do you guys know enough about this to identify which one's the open, the loose, and the topped subunit for the alpha and beta subunits?
I do not know where this is.
So guess, which one of these beta subunits do you think is going to be more constrained and more tight?
The one with the,
Which one? This one? This one?
that one.
This one. That's correct. This is the top form, right? Because the gamma subunit has a piece of it that's kind of like sticking out and like making it more tight. So this is the tight form.
So the top one's O and the right one's left.
Correct.
Loose.
This is O, and this is loose. So what is going to be in each of these primarily as far as the ATP goes? Which one will have ATP in it? Which one synthesizes it? T. That's right. So T is where ADP plus PI converts into ATP. Okay. And remember, so I drew the arrows going both ways. This reaction can work backwards. So it can pump protons out in order to break down ATP. We talk about it as an ATP synthase, but it can work the other direction. Okay, so this one, taut is where ATP is. So if taut doesn't help you remember it, so this is taut, you can also think of it as being the transition state. Transition ADP to ATP. Okay. The other two are going to both have ADP and inorganic phosphate in them. Which one releases ATP to rebind ADP? So one of these can have either ATP or ADP. It exchanges it after ATP has been made. ATP is exchanged out for ADP and inorganic phosphate. Which one's going to have that? Correct. O will have it. So ATP will be released, ADP will be bound. So this is locked, is how I remember it. It's technically called loose. I remember that it's locked. So the ATP, or the ADP and inorganic phosphate are now locked inside. They can't leave again. This is open for exchange. Okay. And the way this works, if you hadn't picked up on it already, is that the gamma subunit is going to be rotating counterclockwise. So what is currently taut will next become open, will next become loose, will next become taut, and we'll go through that cycle. As this rotates around, so it takes 3 protons approximately, slightly more than 3. So for a 10 subunit C ring, it will take 3.3 protons for the gamma subunit to turn from this one to this one, which is where we get that it takes 3.3, so I guess I should be writing this on the board instead of just saying it. So for a 10 subunit ring, it takes 3.3 protons to make 1 ATP. So how many protons does 1 NADH end up pumping across the membrane? Do you guys remember? Harkening back to the electron transport chain stuff we talked about last week. How many protons will 1 NADH pump?
4.
So it pumps 4, so in complex 1, it pumps 4. Does it pump any in complex 2 for NADH?
No.
Okay. What about in complex 3?
Oh, is that the same NADH?
Huh? Yeah, so complex 1 breaks down NADH and generates QH2. How many QH2s does it generate? Let me double check. Yeah, it's just one. Okay, so it generates 1 QH2. So how many, let's make this not complicated for a second. How many total protons are pumped for 1 cycle in complex 3? We just had it on the board, like, there's 4, right? So 4 total are pumped, but you only make 1 QH2 here. So you actually, this is where I was saying last week, it gets a little funny and complicated. Technically for 1 NADH, you only pump 2 protons, right? Because you need 2 QH2s to be generated before you can pump the full 4. So you get 2 protons, 4 protons, and then how many ATP does complex 4 pump? 4. Yeah. Holding up his hand. Okay. So you get a total of 10 protons pumped, approximately. So by this logic, you should be generating 3 ATP for every 1 NADH. Now, it's not a completely efficient transfer, right? Some of those protons get used up for other things. Sometimes, I mean, you have the weirdness of the Q cycle a little bit, so that's why we end up breaking it down to approximately 2.5 ATP per NADH. Yeah, Caleb.
Is it the other way around for 3 and 4?
No.
No, I just had it backwards. Okay.
Yeah.
Okay.
That's fine. Yeah. No, they both pump 4, but you technically have to have 2 QH2s
3.
to make 3
Okay.
to pump 4. So you get 2.
Okay, I think it's for
Why the math's funny. So does this make sense? How many ATP are generated? And then when you lose these 4 ATP, then you have 6 protons that are pumped for FADH2, which is why you only get 1.5 ATP for FADH2, because you lose these 4 protons that are going to drive another round of ATP synthesis. Okay, so does that make sense? Okay. So yeah, need to just kind of understand the different subunits, how they function, things like that. Great. All right. So yesterday in class, you guys got a handout that was maybe a little confusing. I don't know. Maybe you guys felt like it was totally clear. I felt like it may have been confusing, so I have put the 2 shuttles we talked about in class yesterday on here, but I used different images for them because Coop was complaining about the images that were being used. Oh. Are there enough there too? Okay. So, what are the names of the 2 shuttle systems that are on this handout that I just gave you? Malate what? What's it called? It's malate aspartate. So it's malate aspartate shuttle. What's the other one? Glycerol 3-phosphate shuttle. Yeah. So those are the names of the 2 shuttles. You need to understand which one of them is more efficient. So do you remember you had a clicker question about that? Which one of these is going to be more efficient? Malate. Yeah. So the NADH that's generated in glycolysis, as you can see in the glycerol 3-phosphate shuttle, it actually ends up entering the electron transport chain as FADH2. So you lose essentially 1 ATP from the NADHs that are generated in glycolysis. Okay. So what I want you guys to do, you can see these giant white boxes. I want you to write in the enzyme names, or in the case down here, the complexes in the membrane that is entering for the electron transport chain. We'll talk about that in a second. I want you guys to start working on your own. Can I erase this? Nobody's screaming. I'm going to go ahead and do that.
Nope. Sweet. Hey, what time are you guys going up there? 2 years are definitely filtering if Mitch is going. Okay, cool. I can rub my eyes today and put on eye makeup. It's the best day ever. My basket over the past 4 days because I've had so much crap to do it. And Ben said he was going to meet us up there. I was thinking about waiting for him, just camping on Saturday night and then coming back, but on Sunday, it's supposed to be cold, and I have a ton of homework, like so much homework, because I don't know what I've been doing, but I have a ton of stuff, and I'm retaking GRE next Thursday, so I feel like maybe I should study again. So I don't know, maybe I'll just come with you guys and he can meet us there and I'll come back. I feel like he's been married. Oh, really? So you might camp at a secret spot. Oh, fun. Oh, nice. I have to be careful about getting too drunk. We had to be quick. Too drunk. That's not
You guys lined up with my answer key.
What?
I don't have it sitting up here. Oh wait, maybe it's in here. No?
Sneaky if that's the same.
No? No, there should be one of these. Maybe I left it on my printer. There should be one of these that has all the enzyme names on it. I can look them up in the book. It'll take me a second longer. Nobody's gonna fess up to having it. So. All right. Well, what is the enzyme for the glycerol 3-phosphate pathway? What's it called? Yeah. So there's a cytosolic G3P dehydrogenase. So you could do G3P. You can also abbreviate GAP, right? Oh wait, actually, maybe doing that wrong. We'll just do G3P. Keep it consistent. Okay. So is this enzyme in glycolysis?
Yes.
There's a very similar one, but it's actually not. And it's important to remember that. Because the enzyme in glycolysis actually takes glycerol 3-phosphate and converts it into, is it glycerol 1-phosphate?
I think glyceraldehyde.
Or glyceraldehyde, thank you. Glyceraldehyde. Thank you. So it's actually different. It's very similarly named though. Okay, so there is a cytosolic form, and then there's a membrane-bound form. It's actually the exact same enzyme. One is in the cytosol and uses NADH. One is in the membrane and uses FADH2. So similar to succinate dehydrogenase, this is a part of complex 2. So on your sheets, where that box is underneath it for you to write the complex, that's the complex it's in. It's part of complex 2, so that this FADH immediately enters the electron transport chain. And then this FADH2 is used to generate a QH2, which then goes to complex 3. Okay. All right. What are, and I didn't draw the other one up on the board because I started looking for my answer key. What are the enzyme names for the malate aspartate shuttle? One of the enzymes you should already know, even if you don't know the other one, because it's part of the citric acid cycle. Malate dehydrogenase is what converts malate to, is what converts malate to oxaloacetate, or in this case, oxaloacetate to malate. So this shuttle system is actually part of why it's advantageous for that awful ratio, right? Because the cell actually wants to be able to easily convert oxaloacetate into malate so that it can pump it across the membrane and thus shuttle it in and out of the membrane, and in and out of the mitochondria so that it can have NADH inside and outside. It's part of the advantage for that awful free energy for converting malate to oxaloacetate. Okay, so, I don't know why I'm picking that up. What is the name of the enzyme that